Okay guys, let's talk about 9.9. 9.9 is pretty straightforward overall. I did 1b, 2b, and 3a on here. For 1b, it said take your function and turn it into a geometric power series. In order to have a geometric power series, remember you need it in the form a over 1 minus r. While a and r can be anything, you are fixed on this number being a 1. So what is it right now? It's a 5. So in order to get that to a 1, we have to divide all terms by 5. So 2 divided by 5 is 2/5. 5 divided by 5 is 1. X divided by 5 is just x over 5. And now we are in the right form, and we can turn it into an infinite series, a times r to the n. Here our a is 2/5. Our r is x over 5. So it's the sum from n equals 0 to infinity of 2/5 times x over 5 to the nth power. That's it. Pretty basic. 2b is a little bit more work. On 2b, you notice that the denominator is a quadratic, but it is a quadratic you can factor, and so you need to break it down using partial fraction decomposition into two different fractions that we can apply a over 1 minus r to. Now when you factor, you get 3x minus 1 times x plus 2. And when you separate a over 3x minus 1 plus b over x plus 2, and you solve to find your partial fraction decomposition, you get b ends up being 2 and a is negative 3. So that means negative 3 over 3x minus 1 plus 2 over x plus 2. That is this function broken down. But the rules still apply that applied to the first problem. We still need both of those in a over 1 minus r form. Now, the first one's kind of easy, but a little bit of a trick. You can either do it by multiplying negative 1 over negative 1 to switch them, which then becomes positive 3 over 1 minus 3x, or you can take this negative, factor it out, and distribute it to the denominator. It's exactly the same thing. For the second one, of course, we need the constant first, so it becomes 2 over 2 plus x, which is 2 minus negative x. This one already has a 1 where it's supposed to, so it's fine. But this one needs to divide everything by 2 in order for the denominator to have a 1. So you do that, and you get both of these in the proper form, and you can convert them into their infinite sum. Now, one thing to note, this problem also asks you for the interval of convergence. Now, in order for 1 minus 3x to work, remember our r has to be less, absolute value of r is less than 1. That means the absolute value of 3x has to be less than 1. Now for the second fraction, it only means the absolute value of negative x over 2 has to be less than 1, which means absolute value of x has to be less than 2. So between negative 2 and 2. So you're probably thinking, well, these are different, how do I choose? Remember that it has to work for both of them. Numbers between 0 or negative 1/3 and positive 1/3 will work for both of these, but numbers between 1/3 and 2 are not going to work for this one, and you couldn't use the geometric rule. So you use the more restrictive of the two intervals as far as what r can be, or in this case what x can be. So x can be between negative 1/3 and 1/3. You can check the endpoints if you want, but they never work for this. It's strictly less than. So the only thing we have left to do is to combine both of our functions into one power series. Now, I'm going to combine them together, but I'm also going to separate the coefficients from the x. Here it's a negative 1/2, here it's a 3. So I have 3 times 3 to the n, x to the n, plus negative 1/2 to the n, x to the n. Now notice that these are both 3's. 3 times 3 to the n is just 3 to the n plus 1, times x to the n plus negative 1/2 to the n, x to the n. If I factor out the x to the n on the outside, I just leave these two together in a fraction. There's really nothing else I can do with those. So your final summation is a summation from n equals 0 to infinity of 3 to the n plus 1 plus negative 1/2 to the n, all times x to the n. And again, the interval of convergence is from negative 1/3 to positive 1/3. Now one note on 3a, down here at the bottom, it says h of x equals 1 over 1 plus x minus 1 over 1 minus x, and it gives you the power series for what it is. So 1 over 1 plus x is negative 1 to the n, x to the n. 1 over 1 minus x is just the classic x to the n. Now they're subtracted. So again, just like I did in the last problem, I can combine them into one form. So it's negative 1 to the n minus 1 all times x to the n. Now, a little note how we clean this up. When n is even, -1 to an even power is 1. This whole thing becomes 0, which means all of the even terms are going to die. Now for n odd, -1 to an odd power is -1. -1 minus 1 is -2. So every odd power is going to have a coefficient of -2. Since all the even powers are gone and all the odd powers have the same coefficient, we can simplify this even further. From n equals 0 to infinity, -2 times what ends up being x to the odd. The way we represent even numbers is 2 times n, because if you double any number, it's going to be even. However, if you want odd numbers, you need to do 2n plus 1. Now, I would accept both of these answers, but this is really a more cleaned up version of the answer. And that's all of our homeworks up to this point.